All right, everybody, welcome to the video here for lesson number 9 on the law of sines. This lesson is actually going to be taught over the course of a couple days. All right, so just watch the video for whatever you need for the current lesson that you're on for this day. Fast forward to the point where you need it if you're on a future lesson, or rewatch it if you are confused about what we're doing here for the law of sines. So one of the things that happens with right triangles is you can always use sine, cosine, and tangent ratios to find the length of missing sides or the size of missing angles. But that doesn't apply to triangles that are not 90 degrees. So the opening exercise gives us a triangle. It gives us 3 angles, and it wants us to find the side of DE to the nearest hundredth. Well, looking at it upon first glance, I start to look at opposite sides, adjacent sides, and all of that stuff. But unfortunately, because this is 91 degrees, it's not a right angle. So if we were to even find angle E, so if I was to do 180 minus 91 minus 22, I see that angle E is 67 degrees. So because there's no 90-degree angle, there's no hypotenuse. All right, so can we answer this question? The answer is no. And the reason why we can't use basic trig or the Pythagorean theorem is there's no right angle. So mathematicians were puzzled by this. We need to be able to find missing sides of triangles that aren't right triangles. Not every triangle ever drawn has a 90-degree angle in it. So they started looking at some of the things that were common, and I noticed that there is a way of doing it. All right, and that's what we're going to be learning about in this lesson. It's called the law of sines. So the law of sines can always be used to find a missing side or an angle of any triangle. It's a relationship between the side and an angle using sine, thus the name law of sines. So there's a ratio here that we know, which is the side divided by the sine of an angle is equal to another side divided by the sine of that angle divided by the third side divided by the sine of the angle. Now we're only ever going to use 2 of these 3 fractions at one time because we want to create a proportion. So we want to pick the correct proportion to use. So let's go back to the opening exercise. So we had already found that angle E was 67 degrees. So what we're looking for is what I like to call matching pairs. So I'm looking for an angle that has a matching side. So a side opposite it. An angle that has a matching side. So those are the sides and the angles that I'm going to use. But neither of those would give me a variable. I want to know DE. I want to know X. So here's another matching side that I have. So I have 3 different proportions, 3 different ratios I can set up, all right? And I want to choose 2 of them so that one of them has X in it. So I know for sure one of the proportions I'm going to use is X over the sine of 91. Because I want it to have X in the equation. The other ratio I'm choosing doesn't matter. I can either choose 16.55 divided by the sine of 67 or 6.74 divided by the sine of 22. Either way, I'm going to get the same exact value for X. If you don't believe me, do it both ways and you'll see you will. So I'm going to use 6.74 divided by the sine of 22. Cross multiply. So I get X sine of 22 is equal to 6.74 sine of 91. Notice I'm putting the side length 6.74 in front of the ratio of sine of 91. It's just easier to type in the calculator that way. Divide both sides by the sine of 22. And whatever this is in my calculator is my answer. All right, so if I type that all in one shot, 6.74 sine of 91, end your parenthesis, divided by the sine of 22, end your parenthesis, I get a side length of 17.99. It says nearest hundredth, so we'll go to there. Now you might be saying, how does this work, right? Other than me going through and doing a whole big long proof and dividing this triangle up into right triangles to prove it to you and spend like 30 minutes showing, just believe me that it does work, right? But it does come down to making right triangles within this non-right triangle, which is why the sine is in there 2 different times, right? So it's kind of just looking at a ratio there in that aspect of it, all right? So let's keep going. So number one says in triangle ABC, angle A is 33 degrees. Side A is 12. Notice this is a lowercase a, so that represents side A. So when I draw my triangle, so here's triangle ABC. Angle A is 33. Side A is opposite angle A, so that's 12. Angle B is 43 degrees, and we want to know the length of side B. So again, I'm looking for matching pairs. 43 matches with B, 33 degrees matches with 12. So I have a good set of matching pairs. I have a variable, and I have another set of matching pairs that has numbers in it. So I can say B divided by the sine of 43 is equal to 12 over the sine of 33. Cross multiply, I get B sine of 33 is equal to 12 sine of 43. Divide by the sine of 33. Those cancel, and B comes out to be whatever this is in my calculator. All right, so type it in, see what we get. Again, you should be typing this in with me. Don't just wait for me to type it in. All right, if you forgot your calculator at home, at school, and you're trying to do this at home, use a calculator online or something. Practice typing it in. It's not good enough to just watch what I'm doing. All right, nearest hundredth, so 2 decimal places. Let's try another one. In right triangle PQR, it says angle Q is 90, so P and R are just in the other two spots. Angle P is 57. It says side P is 9.3, so that's the side down here. And it wants us to find side Q. Now, we totally could use regular SOHCAHTOA for this, right? I could say it's a 90-degree angle. 57 is my angle. Whoops. I don't know what I hit there. Sorry. I could say 57 is my angle. 9.3 is opposite. Q is hypotenuse. I could just use sine here and get the same answer, right? But we're in the law of sines lesson, so let's use the law of sines. So we have an angle points to a side, an angle points to a side. So we have a good ratio. So I have Q divided by the sine of 90 is equal to 9.3 divided by the sine of 57. Cross multiply, I get Q sine of 57 is equal to 9.3 sine of 90. Divide both sides by the sine of 57. Those cancel, and Q is whatever that comes out to be in my calculator. Now, the interesting thing about this question, and I believe the reason why we put it in there, was to show you that the sine of 90 is actually 1, but that's something we'll learn a lot more about in Algebra 2. Nearest tenth, so that's 1 decimal place, so 11.1. But just use the law of sines, or if you want to, revert back to SOHCAHTOA, right? So number 2 is a good question because it's showing you that if you don't like SOHCAHTOA and you like law of sines better, you could use law of sines for every single question that I ever give you, right? If you like SOHCAHTOA better, if you see a right triangle, use SOHCAHTOA, right? But law of sines can be used when we don't have right triangles, like number 3. So number 3 gives us triangle XYZ. I know it's not a right triangle, so it doesn't tell me. Y is 87, so unless the other two angles are super small, it's not going to be a right triangle. Side Y is 14, so that's opposite angle Y. Side Z is 12. And this wants us to find angle Z. So we have our matching pairs. I have 12 divided by the sine of Z, and I have 14 divided by the sine of 87. Same idea, but our variable's in a different spot now. So we just got to do a little bit more thinking once we start solving this, right? The other kind of teaching point I can give you here is draw your z's with a little slash through it so they don't look like 2's, right? But hey, if you have z's that don't look like 2's, that's fine. Mine always look like 2's, so I always put little slashes through them. So if we cross multiply, we have 14 sine of z is equal to 12 sine of 87. Now, I want to get it so that the variable's by itself. So I can't divide the sine of z to the other side like I've done in the previous examples. I'm going to divide away the 14. and I'm going to get the sine of z is equal to whatever that is in my calculator. So 12 sine of 87, and your parenthesis, divided by 14, and I'm going to get a decimal. Not my answer yet, so I don't want to round it yet, so I'm going to leave it in my calculator. Now, one of the things that we learned throughout this whole chapter is if I want to find a side, just type it in your calculator. But if I want to find an angle, I got to do a little bit more thinking. I have to get z by itself by using inverse sine. So there's always that one extra step. So if we do second sine of that previous decimal we had in our calculator, we get an angle here to the nearest tenth of 58.9 degrees. It's about as hard as I'll get, to be honest with you. Let's keep moving. So here's my famous water tower question. I do this question every year. It's the same idea here that we've been looking at, but we do have to do a little bit of thinking here. So it says a fire breaks out 80 feet from the ranger tower. The ranger needs to run to the water tower to fill up a spout, and we want to be able to flood and put out a fire, right? How far is the run from his tower to the water tower? So I don't know that, so that's x. Now remember, I keep saying we want these matching pairs. Here's a matching pair. I want x to be in my proportion. So to get x, I would need this angle to be a matching pair with x. But I wasn't given that angle. I was, however, given the other two. So we have to think, how many angles are in a triangle? This is 180. So if I subtract 46 and subtract 28, whatever's left over there winds up being my remaining angle. So I have 106. So what are my matching pairs? I have x over the sine of 106 is equal to 80 over the sine of 28. Do some cross multiplying. So I have x sine of 28 is equal to 80 sine of 106. Divide by the sine of 28. Those cancel. And type that in your calculator. See what you get. Just make sure when you're typing these in, you're ending parentheses when it's appropriate. All right. So I get 164 feet. All right. It says nearest foot. So that makes sense. Number 3 gives us this kind of weird looking picture. So we have 2 lighthouses. They're 30 miles apart. And each of them makes an angle. So there's a 40-degree angle from this first lighthouse to get to this boat, and a 32-degree angle from this lighthouse to get to this boat, right? Now notice neither of those 2 angles are in this nice triangle that we have drawn here in our picture. But since there's a 90-degree angle between the shoreline and the line of sight from one lighthouse to the other, I know this is 50 degrees. And I know this is going to be 58 degrees because 90 minus 40 is 50, 90 minus 32 is 58. And if I take 180, subtract 50, and subtract 58, that gives us 72 for the remaining angle. Now, it wants us to find some distances, right? So it wants us to find the distance from the boat to each of the lighthouses when the time it was spotted. So I'm going to make an x here, and I'm going to make a y here. I can't use Pythagorean theorem. I can't use SOHCAHTOA. I don't have a right angle. But I can use the law of sines twice, once to find x and once to find y. So the ratio that I want to use here for x is going to be x over the sine of 58. And I want to use a ratio that's a matching pair here that has numbers in it. So 30 miles over the sine of 72. The ratio I'd want to use to find y is going to be y over the sine of 50 is equal to 30 over the sine of 72. So I'm solving 2 problems that look very similar, that use some of the same numbers. They just have a different ratio as one of the parts. So let's solve for x first. Cross multiply. X sine of 72 is equal to 30 sine of 58. Divide by the sine of 72. and we get whatever that comes out to be in my calculator. So we get nearest mile, so that would be 27 miles. Do the same thing to solve for y. I just have some different numbers, so I'm going to wind up getting a different result. And we can figure out, well, which lighthouse is closer to the boat, right? So if I do the same thing here, but it's the sine of 50 instead of 58, I get 24 miles, right? So I could say this lighthouse is further away than this lighthouse. All right, moving right along. Here's a couple of Regents questions. Now, sometimes Regents questions are set up in a way where you could actually use the SOHCAHTOA method or Pythagorean theorem, but it might just take longer. This is one of those questions. So I could totally use SOHCAHTOA here if I really wanted to. It would just take a little bit of effort, right? We'd have to put variables in weird spots, and it would just be a mess. To use the law of sines would make this much quicker and actually a little bit of an easier question. So it says, Kathy wants to determine the height of a flagpole shown in the diagram below. She uses a survey instrument to determine the angle of elevation from two different spots. So one is 52.8 degrees and one is 34.9 degrees. They were not nice to us. They gave us some pretty cruddy decimals there. She walks 8 meters from one spot to get to the next location, so that's where that 8 meters comes in. And she's keeping the instrument 1.7 meters above the ground. Determine the height of the flagpole. So whenever I don't know something, I want to use a variable, so I'm going to put x here. But just keep in mind, this is 1.7. So whatever I get for x, I'm going to add 1.7 to it to get the height of the flagpole. That was a mistake that a lot of kids made on this. Now, the problem is, I need to know a side of that right triangle with the 52.8 degree angle. I need to know this side. Why do I need to know that side? Well, that's the side that's common between the right triangle and this weird looking obtuse triangle over here. So I'm going to label that side y. So in that obtuse triangle, I have one matching pair. I have this angle, which points to this side. So I could say y divided by the sine of 34.9 is equal to. Now I have a side, but I don't know this angle up here. So I need to find that angle. So we need to do some thinking. So in this picture, I have a 52.8 degree angle that is a linear pair to this obtuse angle. So if I do 180 minus 52.8, I get 127.2. That angle's not going to help me set up a ratio, but it is going to help me find this little tiny angle up here. Because I know the three angles of a triangle have to add up to 180. So if I subtract 180 minus 127.2 and minus 34.9, I know this little angle is 17.9 degrees, making the matching pair between that and 8. So now I could say the other part of my proportion here is 8 over the sine of 17.9. Do some cross multiplying just like we've been doing the whole lesson here. Divide by the sine of 17.9. And we get y is equal to whatever that is. So if I do 8 sine 34.9 and my parenthesis sine of 17.9, I get some messy number, 14.892. Now, the reason why I'm not rounding that to nearest tenth is that's not the height, but it's going to help me find the height. So let me just redraw my triangle here. So here's my right triangle, x, 52.8, and the side we just found, y, is 14.892. Well, I could just use regular SOHCAHTOA, right? I have the opposite side, I have the hypotenuse side, so I could say the sine of 52.8 is equal to x over 14.892. Multiply both sides by 14.892. These cancel. And I get x is equal to whatever that is in my calculator, 14.892 times the sine of 52.8. So that gives me 11.9. And that 11.9 isn't the height of the flagpole. The height of the flagpole is 11.9 plus the 1.7 that showed where the height of this mechanism was that measured those angles. So if I do that plus 1.7, I get 13.6, which is the actual height of the flagpole. I'll be honest with you, that is the hardest trig question I've ever seen on a geometry regents exam. There's a lot going on there, right? So if you didn't fully get that, I'm not that stressed about it, okay? Now, in the previous lesson, we did the same lighthouse question. And what we did to do this lighthouse question was we did SOHCAHTOA twice, we did some subtraction, and we could actually solve this a little bit easier using the law of sines, or differently using the law of sines. I'm not going to go through it because I'm going to be honest with you, I want you to just use SOHCAHTOA, right? I only want you to use law of sines if you absolutely have to be honest, right? So if you really want me to do this for you, just come and see me when I get back, and we will go over it together, but this is unnecessary for us to do, so we're just going to skip it. All right, let's go to homework. Let's practice the law of sines a little bit more. So in triangle bug, I see that angle B is 78, angle G is 42, and side G is 99. And we want to find side B. So I could say x over the sine of 78 is equal to 99 over the sine of 42. Cross multiply, and just keep going just like we did in class. So again, we want to use the law of sines when we have to use the law of sines. This is an example when we have to use it. There's no right angle here. I can't do anything else, right? If I see right angles, I want you to use SOHCAHTOA. So we have 99 sine 78 divided by the sine of 42, whatever that comes out to be. So we see side B is 144.7. Okay, let's find another missing side. So we have triangle XYZ. Angle Y is 125. Angle X is 18. Angle Y is 112. And it wants us to find side Z. I don't want to use X here, so I'll just use A. Or let's just use Z, actually. All right, now to do that, I need to know this angle. So if I do 180 minus 125 minus 18, I get this angle is 37. Because remember, I'm looking for these matching pairs, right? I want angles that match opposite sides. And I want the side Z to be in my problem. So I have Z over the sine of 37 is equal to 112 over the sine of 125. Cross multiply. Z sine of 125 is equal to 112 times the sine of 37. Divide both sides, and we can figure out our answer. Type that in our calculator. And we get round to nearest hundredth, 82.28. Perfect. All right, let's take a look at this next one. So it says a baseball fan is sitting directly behind home plate in the last row of the upper deck. The angle of depression to home plate is 30 degrees. The angle of depression to the pitcher's mound is 24 degrees. The distance between the pitcher's mound and home plate is 60.5 feet. So this is 60.5 feet. I have two angles of depression, one to home plate and one to the pitcher's mound from this fan's crazy seat all the way up in the upper deck. So to get from his eyesight to home plate, it was a 30-degree depression. Let me just use a different color here. It'll help see it a little bit better. From his eyesight to the pitcher's mound was 24 degrees. So the angle between these two sides of the non-right triangle here is going to be 6 degrees. All right, all I'm doing to get that is I'm subtracting the two different angles of depression. It then says the distance between a pitcher's mound and home plate. So how far is the distance from the fan to home plate? So that's x. But notice we only have one angle. But there's something that we learned in the angle of depression lesson. The angles of depression are created by parallel lines. So this fan's eyesight and the horizontal distance between home plate and the pitcher's mound, well, they're parallel to each other. So if that angle's 24 degrees, this angle's also 24 degrees. So what I realistically have, if I look at this triangle, not in this crazy looking picture, I have a obtuse triangle with an angle of 6, an angle of 24, a side of 60.5, and a side that we don't know that I want to know. So I could set up a little proportion here, right? I could say x over the sine of 24 is equal to 60.5 divided by the sine of 6. And again, I want to use the law of sines here because I don't have a right angle. There's no other way for me to solve this using what we know about trigonometry right now. So we can only use the law of sines here. Divide both sides by the sine of 6, and whatever that is going to be that fan's distance. So 60.5 sine of 24 divided by the sine of 6. And we see he is nearest foot, so 235 feet away. It's a realistic answer. All right, so moving right along here, right? So again, like I said, this is going to be over the course of a couple days, right? So this is all not going to be a one lesson. So if this is not your homework assignment, essentially, is what I'm saying here. So you want to pause the video or go back to it tomorrow, that's fine. So the next question here talks about some extra trig application problems. So these we can kind of use whatever trigonometry we know to solve. So we have this this boat sitting on the ocean surface. There's an angle of depression of 67.4 degrees to the ocean floor. It says the probe travels approximately 39 meters at an angle of depression of 67.4. So that dotted line, that angled line, is 3,900 meters. So it wants us to figure out how many meters below the surface of the floor is the probe going to reach. So I want to know the vertical distance between the probe and the ocean surface, right? So the probe's on the ocean floor. I want to know the vertical distance. So I'm going to put in a vertical line here, make a right angle, and we want to know that vertical distance. So what I realistically have, if I wanted to redraw this triangle so it looks like the ones we did in class without being a word problem, I have an angle of 67.4, I have a side of 3,900, and I have a side of x. That's all I'm asking you to do here, right? It's regular SOHCAHTOA. This is the opposite side. This is the hypotenuse. So it's just a sine ratio. So I could say the sine of 67.4 is equal to x over 3,900. This distance should be less than 3,900 because the hypotenuse should be the longest side. Multiply both sides by 3,900. And we get x equals whatever that comes out to be. So 3,900 sine of 67.4. And this wants us to round to the nearest 100 meters. So we get 3,600.519 ... To round up to nearest 100 meters, I could either round to 3,600 or 3,700. Well, this is way closer to 3,600. So my answer here is approximately 3,600 meters. Number 2 talks about Tim designing a roof. The roof is in the shape of an isosceles triangle. Each angle at the end of the truss is 18.5 degrees, as shown in my picture. And it says if the horizontal base of the roof truss is 36 feet across, what is the approximate height of the roof? Well, if this whole distance is 36 feet, and it's isosceles, that means each of these smaller distances are 18. And I want to find the height. So realistically, I really only care about one of these right triangles. I don't care about both. So I have an angle that's given, I have an opposite side that I want to know, and I have an adjacent side that I do know, so that's a tangent ratio. So I say the tangent of 18.5 is equal to the opposite side over the adjacent side. Multiply both sides by 18, and I get x equals 18 tangent of 18.5. which to the nearest hundredth is 6.02 feet. Not too bad. Number 2 says that we have this radio tower is anchored by long cables, and we have this kind of weird looking picture. So it says point A is 250 feet from the base of the tower. It then says if the angle of elevation from point A to point D is 71 degrees and the angle of elevation from point to point B is 65 degrees, find the distance between B and D. Now, this is a tough question, right? Because of the picture, right? So we have to do a little bit of thinking here. So let's just look at triangle ABC for a second. So here's triangle ABC. A, B, C. What do I know about triangle ABC? I know a side of 250. I know angle A to angle B. So from angle A to angle B, it says is 65 degrees, meaning I can find the distance from B to C. Let's take a look at triangle ADC. So I know the angle from A to D is 71 degrees. I still know AC is 250 degrees. Still a right angle. So I can find the distance between D to C. So that's different, so that'll be Y. What could I do with X and Y to find this little piece? Well, I know I just made this whole big thing Y and this whole small thing X. So if I subtract Y and X, I can find dB. So realistically, this is just a double trig problem. Could you use the law of sines for this question? Sure. It'll be more difficult, so I wouldn't. I would just use this regular SOHCAHTOA ratio stuff that we know. So since both of them have the opposite side and the adjacent side labeled, I'm going to use tangent twice. So I'm going to say the tangent of 65 is equal to the opposite side over the adjacent side. Multiply both sides by 250. So I have 250 tangent of 65. So X, which is the shorter piece, is 536.127. And then if I do the same thing for Y, right, I can say the tangent of 71 is equal to Y over 250. Multiply both sides by 250. And we get Y is equal to whatever that comes out to be. It should be a longer distance. So 726.053. Now you might be saying, why are you rounding there? It asks us to round to the nearest meter. Well, I don't have an answer yet, right? My answer is this difference between those two lengths. So I want to wait until I find the actual distance to round. So now if I do some subtraction, so if I subtract the bigger value from the smaller value, or Y minus X, I wind up getting 190 meters. Not too bad, right? And that's it, right? So that's our law of sines / practicing some SOHCAHTOA and more challenging questions. And that's basically trigonometry, right? Everything we've learned up to there is everything we'll talk about with trigonometry. You'll see the next lesson is talking about some special right triangles. This doesn't come up as often in our Regents exam, but these are great SAT questions, so we'll talk about those in lesson 10. But we're getting really close to your test on this chapter, so start reviewing, start looking back. If you want to, even start making your study guides, right? There was a lot that we learned in this chapter. You might think it's easy, you might think it's challenging, I'm not sure, right? But for sure, we want to start reviewing and looking at some of the stuff we did at the beginning of the chapter as well. All right, good luck, and I'll see you guys all